All right, let's just get right into it. Welcome to this explainer, where we're going to unpack something truly fascinating. We're looking at how a tool called DuckDB is completely disrupting the data science ecosystem, and honestly, challenging literally everything we thought we knew about big data. If you work with data, or even if you just want to understand how modern businesses are running under the hood, this explainer is going to completely change your perspective. To really understand the core problem with traditional data analysis, we kind of have to look at the massive amount of tedious setup required just to ask a totally basic question. Imagine you've got an open data set about Dutch railways, and you just want to find out which train stations had the worst delays over a random weekend in February. Sounds simple enough, right? Well, in legacy database systems, you'd have to download the file, unzip it, inspect the contents, spin up a server, connect a client, and then painstakingly spell out the exact data type for every single field before you can even write your query. It is a massive headache.
The contrast is absolutely wild. Asking that simple train delay question in traditional SQL takes over 750 keystrokes just to define the schema and actually get an answer. But with DuckDB, you're using modern SQL. You literally just point it at a remote URL, and the system automatically downloads it, decompresses it, auto-detects the CSV dialect, infers the schema, and runs your query, all in about 200 keystrokes. We are talking about a 70% reduction in typing.
So let's see how this builds into a much larger story about how we handle information today. We can map this journey of data processing kind of like that Galaxy Brain meme, moving through increasing levels of efficiency and enlightenment. We start down at level 1, the tiny duck brain, dealing with plain text files like CSVs. Look, they've been around for 50 years, but they are incredibly slow, they're super prone to encoding errors, and they read data row by row, which is just terrible for analytical queries.
Moving up a level, we finally ditched those slow row-based plain text files for column-based binary formats like Parquet. Instead of reading across a row like an old-school tape drive, column-based storage lumps all the data of the exact same type together. So all the dates are together, all the delays are together. This allows for some beautiful compression. It basically means you can query that exact same railway data set in about 1 single second, simply because you're only scanning the specific columns you actually need.
Now, things get really serious at our third level, the database. By moving that data into a specialized analytical database like DuckDB, your query time plummets from 1 second down to a blistering 0.01 seconds. Everything is safely encoded, it's perfectly type-checked, and crucially, unlike a static flat file, a database is completely updatable.
And that ability to update data is absolutely crucial. There's this wild true story from the source material about certain, let's say, sneaky European railway operators who were caught actively renaming their delayed trains in their databases. Why? Because when frustrated passengers opened their apps to request a refund, the app would look for the original train number, hit a 404 API error because the train was quote-unquote gone, and the claim would just fail. You simply cannot pull a fast one like that with a static Parquet file, but in a database, a quick little update saves the company a fortune in compensation.
So if databases are this fast and powerful, why did data scientists actively resist using them back in 2018 when DuckDB was born? Well, because traditional databases were a massive operational headache. They were ridiculously expensive, totally clunky, and required 60-minute configuration sessions just to grant basic permissions. They completely lack the smooth, auto-detecting user experience that data scientists had come to love in Python tools like Pandas.
So the crucial point here is that the creators of DuckDB recognized they had to completely solve this usability problem to win people over, and they did it by adopting SQLite's in-process model. Instead of spinning up some massive server that you have to connect to over a network, DuckDB runs entirely inside your Python script or directly on your laptop. There is absolutely zero network overhead. You literally just install a library and boom, you have a hyper-fast analytical database running immediately. They also obsessed over the user experience, introducing these quality-of-life features that might seem small but are huge time savers in practice. Things like allowing a trailing comma at the end of a SQL list without breaking the whole query, or introducing the group by all command so you don't have to sit there manually typing out every single non-aggregated field. This usability focus was such a massive hit that industry giants like Snowflake, Databricks, Oracle, and Postgres actually ended up copying the features. Which brings us to a really fascinating shift in perspective. Are we completely overrating the era of big data? Think about it. Back in 2008, hardware was pretty weak. A standard laptop had spinning hard drives and weak CPUs, so to process lots of data, you absolutely needed complex, expensive server clusters. But the hardware of today, it is completely unrecognizable compared to a decade ago.
These benchmark cost comparisons over the last decade are genuinely mind-blowing. The TPCH benchmark is basically the gold standard for testing database performance. Back in 2012, processing a 1 terabyte dataset required a beautifully orchestrated enterprise server rack from Dell or Oracle that would set you back $500,000. Today, you can attach an NVMe SSD to a tiny little Raspberry Pi for about €300, and it handles that exact same terabyte of data effortlessly. For €3,000, a modern framework laptop can process 10 terabytes. The hardware caught up, meaning you often just don't need a massive distributed server cluster anymore.
To prove just how portable and resilient this in-process database really is, the presenter actually ran a database benchmark on a brand new iPhone 17 Pro while it was fully submerged underwater in a sink. Obviously the cooling was great, but the test ultimately failed for a pretty hilarious reason. The water blocked the Wi-Fi radio waves so they couldn't communicate with the phone. But the database itself, it handled the data processing without breaking a sweat.
So how exactly does it run so fast on a phone or a laptop? DuckDB achieves this localized speed through something called lightweight indexing. It chops your data into groups of roughly 100,000 rows. For every single column in that group, it records the minimum and maximum values. So if you're looking for train delays greater than 2 minutes, and the index says the maximum delay in a specific chunk is only 1.6 minutes, DuckDB just completely skips downloading or scanning that chunk. It saves massive amounts of time and bandwidth.
But look, to reach peak data enlightenment, we have to look objectively at DuckDB's flaws too. It is strictly a single-player experience. If one user is writing data to the file, it locks the whole file, completely blocking everyone else out. It's also pretty slow if you try to insert data one single row at a time. And if you try to scale up massively, you run into hard architecture limits. For example, a 100 terabyte experiment yielded a single 27 terabyte database file. You can't even put a single file that large into an Amazon S3 cloud bucket because S3 literally has a 5 terabyte limit per file.
This brings us to level 4 in our Galaxy Brain evolution, data lakes. To solve that scale issue, the industry started storing huge amounts of Parquet files in cheap cloud object storage using open formats like Iceberg. Iceberg tracks all those files using, frankly, clunky JSON metadata, which allows you to treat scattered files like a cohesive, updatable database table. Now, it scales infinitely, sure, but it suffers from massive operational complexity and really bad performance issues when you bombard it with small updates.
So, the industry's next fix was the Lakehouse architecture. This essentially places a complicated catalog database right on top of the data lake to manage all that metadata and track the files. It gives you a fully scalable database on cheap storage, but the catch is you still haven't truly fixed the underlying performance issues of formats like Iceberg, and the operational complexity is still incredibly high.
And this logical gap leads us right to peak data enlightenment, Duck Lake. The realization here is actually profound. If you're already putting a catalog database on top of your data lake, why not use that database for all the metadata? Duck Lake completely replaces all that messy, slow JSON metadata with an actual lightweight SQL database sitting directly in the catalog layer.
This architecture is incredibly powerful because Duck Lake acts as a real database and maintains snapshot logs of every single change. It gives you the power of time travel. Remember our sneaky train company retroactively renaming their delayed trains? Well, with Duck Lake, you can query exactly what the data looked like last week. You can see the original train numbers, completely busting the railway's trick to dodge refunds. It's also absolutely perfect for data scientists who need to rerun a script against the data exactly as it existed last Tuesday. Even better, Duck Lake finally solves DuckDB's biggest limitation. If you use a traditional database like Postgres as your Duck Lake catalog in the middle, you unlock a true multiplayer experience. Multiple different DuckDB clients running on different laptops can coordinate through that Postgres catalog, reading and writing to the same massive data lake in the cloud simultaneously without ever locking each other out.
Let's summarize the Duck Lake advantage real quick because it is massive. It elegantly solves the single-player limit by unlocking true multiplayer collaboration. It completely eliminates those unwieldy 27 terabyte single files that break cloud storage limits. Inserts and deletes are suddenly lightning fast because they're temporarily cached in the middle database. And through it all, you retain the blazing fast Parquet file reading capabilities that made DuckDB famous in the very first place.
Now, if you're thinking about diving into this for your own projects, it's worth understanding the ecosystem. It's built to be very safe for long-term enterprise adoption. The core intellectual property and trademarks are fiercely protected by the DuckDB Foundation, which is a nonprofit based in the Netherlands. So if a big tech giant tries to buy the project, the core IP remains completely independent. Meanwhile, DuckDB Labs handles enterprise consulting, and a heavily venture-backed US startup called MotherDuck is building out the massive cloud-native infrastructure for it.
Which leaves us with one final, very provocative question to ponder. We've seen that a cheap, modern laptop can process terabytes of data locally in a fraction of a second. We've seen that Duck Lake now solves the multiplayer and cloud storage scale issues perfectly. So knowing that you can achieve all of this with such lightweight, elegantly designed tools, why are you still paying an absolute fortune to maintain that massive, slow, overly complex big data cluster? It might just be time to reach peak enlightenment. Thanks for joining me on this explainer, and I'll catch you next time.